and in the process, we stabilize smaller particles. These particles still have effect size into them, but now the transformation is retarded, and we see that variation as a function of gel time. And finally, by allowing the gel time to go even longer, to a minute or more, what we do is also grow much larger particle, and at the same time, by allowing the particle to grow more slowly, in a sense, it's a low temperature way to anneal out the defects, and we found that these particles actually resist the tetragonal to monoclinic transformation better, even though strictly on the size alone, there's no difference, or not a large difference in size between these two particles. So I think what I have shown is that by controlling gel time, we actually have an interesting way to control not only particle size of material coming out of the solution, but also the quality of the particles in terms of defect densities. Okay, at this point, in the remaining few minutes I have, I would like to switch gear and again carry this concept a bit further to show you that gel time is an equally important parameter when we try to do two-component synthesis. The specific example that I want to talk about is simply to add silica to zirconia in synthesizing a zirconia silica aerogel. Now, in this case, the zirconia silica precursors have very different reactivity. In fact, the zirconia alkoxide reacts a lot faster than the silicon alkoxide. So in order to balance the difference in reactivity, we adopt a procedure that's commonly practiced in the soil gel literature, namely pre-hydrolysis. Very simply, pre-hydrolysis is to allow the less reactive alkoxide to react with water first so that it can catch up upon the addition of the more reactive alkoxide. We approach this synthesis by doing two series of samples, the non-pre-hydrolyzed step, in which we basically mix everything together, versus the pre-hydrolyzed step, in which the silica precursor is allowed to react with water for 10 minutes prior to the addition of the zirconium alkoxide. Now, having identified gel time as an important parameter in the zirconia world, we actually have to come up with a scheme by which that we can actually isolate the effect of pre-hydrolysis from the effect of gel time. And this is accomplished by the following scheme. We have the following experimental design. For a specific combination of zirconium and silica, we first determine the gel time for a pre-hydrolyzed sample. Okay? We then remove the pre-hydrolysis while keeping all the other conditions the same. Allow the gel time to go to whatever value it is, in this case T prime, which is longer than the gel time with pre-hydrolysis. We add the pre-hydrolysis back on, and then we ask it to as a tuning variable to bring the gel time back to the same value. The best way to appreciate that is actually the bottom graph, in which we are looking at the gel time as an acid ratio, and this is what we refer to as the stair-step synthesis. In other words, at a specific acid ratio, we vary the gel time by taking out the pre-hydrolysis step, and then at each constant gel time, we vary the acid ratio in order to compare hydrolysis versus non-hydrolysis sample. Now, the significance of this experimental scheme, we can actually partition the two effects and allow us to look at it one at a time. Now, without going into too much detail, what I just want to show very briefly is some of the preliminary results by this approach. First of all, when we now look at the BET surface area as a function of gel time, first I have the zirconia sample as a reference that I showed you earlier in the talk, and now here the same result for the zirconia silica 95% sample, i.e. a sample containing 95% zirconia, and the series labeled pH is the one with pre-hydrolysis, and the one that's labeled as NPH is the one without the pre-hydrolysis. So we see several things right away. One is by adding silica, as little as 5% of silica in the zirconia, we actually stabilize the material a little bit in terms of the decrease in surface area upon heat treatment. Also, we show that gel time is again a variable regardless of whether the material has been pre-hydrolyzed in the synthesis. So the last wheel graph I want to show you is that this difference also manifests itself in the pulsar distribution of the material. What we have now here is 3 panels corresponding to 2 series of samples and 3 different gel times. A gel time of about 30 seconds, And as you can see, at each gel time, we can now directly compare the effect of hydrolysis on the phosphite distribution of the material. As you can see, for the series that has been pre-hydrolyzed, the gel time affects the phosphite distribution more so than the series that has not seen pre-hydrolysis. The important point is that again now we have a way to tune these two parameters differently and to try to focus on relating the effect of one on the structural properties of the material after heat treatment. So to summarize, where do we go from here? I hope that I have convinced you that yes, we can synthesize high surface area aerogels as zirconia and silica, and now we have at our disposal several what we call tuning parameters in order to view specific properties in the sample. We are now going to promote these aerogels with sulfate groups and to characterize the behavior of solid superacid. The middle point is actually the message I want to take away from you, for those of you who are interested in soil gel synthesis. The gel time is really a long overlooked parameter, but we feel that it's really the parameter to look at in terms of relating the synthetic parameters to the properties of the material. And at the same time, I think it's a very exciting way to make a multi-component system through tuning these parameters. The challenge facing us is actually to develop techniques to characterize this material and actually understand molecular mixing and mix oxide. So I close by thanking the people who help us with the work, and thank you for your attention.
Thank you very much for your nice presentation. Now, the table is open for discussion. Please.
Alex Bell, University of California, Berkeley. Ed, can you control the synthesis of these bicomponent gels by tailoring the precursor? So that's another direction that you can go, right?
Yes.
Different alkoxylates.
Absolutely.
You'll hydrolyze at different rates.
Absolutely. In fact, the hydrolysis, the question is, can we even tailor the material further on by playing with the alkyl group? Yes, in fact, there are two simple ways to play with the alkyl group. One is to change the size of it, so you can go from a methoxide to an ethoxide to a propoxide and so on and so forth. The other way is even with the same alkyl group, you can bond it with an acetate ligand. So if you do the synthesis by adding some acetic acid to it, you would actually slow it down. So instead of doing a pre-hydrolysis to speed up the slow one, you can do a ligand bonding to slow down the fast one, and it does give you another variable to play with also, yes. And there are many examples of that. And we have tried some too.
And you might have mentioned this and I missed this. If gel time is the parameter, then let's say a gel time is 1 second, whether obtained with a water ratio of 4 or a water ratio of 2, should give you, let's say, equivalent surface areas and other properties. And I don't, did you do that? Did you find out that is in fact the case?
I understand well, at least I think I understand what you're asking. Gel time is interesting in the sense it's not a tunable parameter. I mean, unlike acid or water content, I can just take more or less. Gel time is a consequence of the synthetic parameters, okay? But what we are proposing is you can turn all these other knobs. When all is said and done, that's the marker. So yes, we actually have done that. And for example, when we change the precursor, and it seems that we always come back to, if you compare materials of roughly comparable gel times, it doesn't matter how you get there. Now, but let me qualify that a little bit to be honest. When we say short, intermediate, and long gel time, we are really reporting a range and not a value. All right? So I think I'm quite confident to tell you that if you have material that is like an intermediate gel time, say half to a minute, then yes, if I can either change the acid ratio or the water ratio of the precursor, as long as in that range, with respect to our characterization, we can tell the difference. So I'm being careful here, but because a lot of this, what property technology are you locking on when all is said and done? And I'm telling you that with respect to those that we lock on, gel time seems to be the key.
First of all, I congratulate you to obtain a large capacity area to common dioxide.
Thank you.
The common dioxide usually are very low surface area, so it's very difficult to enlarge the surface area. And at the same time, to stabilize the low temperature tetrahedral to the higher temperature, also difficult. My question is quite simple. Well, have you ever examined the residual some impurities like carbonaceous material, nitrogen oxide or nitrate in the zirconium dioxide after the calcination of 500 degrees? You mentioned about particle size effect on the tetrahedral form by introducing the garlic bubble. Another argument is the contaminant effect on the stabilization of the tetrahedral form. So my question was simple, the contamination by carbonaceous material from the alcoholic compound of such kind.
Okay, your comment is very well appreciated because not only for zirconia, for other oxides, the loss in surface area upon heat treatment is mostly related to kinetics of sintering and crystallization. And it's well known that impurity will do that. So what we observe could be explained by just having impurity retarding the transformation. In fact, one way to stabilize zirconia is to dope it, as you well know. I cannot prove to you that we absolutely have no impurities, but I think what we have stabilized is in fact a material that is pure, and the stabilization comes from the structure integrity through the supercritical drying. Okay? So in fact, we have done it for other oxides, and I guess the ultimate test, and we are going to test that, is when these materials are now used as supports, do we see surprises that could be attributed to impurities? But